In the previous video, we used Riemann's upper sum, meaning we use this area to represent this area to represent this area to represent this, and so on. So we use Riemann's upper sum to show that Sn will always be greater than the natural log of n. Meaning, if you sum up the first nth term, so let's say if you sum up the first 5 terms, then put the 5 into this n here. Put the 5 into this n here. So if you sum up the first 5 terms, meaning the first 5 terms here, it will be greater than the natural log of 5, which is 1.6. So by looking at Riemann's upper sum, we actually show that as you sum up everything from the first term all the way to infinity, we've shown that it will just get bigger and bigger and bigger, because if you take the limit as n tends to infinity, then this is just going to get bigger and bigger and bigger. So we know that, well, we've seen that in the previous video. But by looking at Riemann's lower sum, which we're going to do in this video, by looking at the Riemann's lower sum, you can get more insight into what's going on with the series. So here the upper sum would be this. The upper sum would be you getting the first, so you jump to here, draw across here, so that this here will give you the upper sum. But the lower sum would be you jumping to here and then drawing it straight across here. So this area here, and then the second area would be you jumping to here, jump up here, and so this is us creating Riemann's lower sum. So you jump to here, draw it across. So basically, Riemann's lower sum would be this. Hang on. So Riemann's lower sum would be this. So this area here, well, the first one would be so remember the upper one would be this. This is the upper one, but now we are going to use Riemann's lower sum. So it would be the first term. The first term would be this, and then well this area here would actually represent a half. Because when we come to do the Riemann's lower sum, we actually miss out this first part here. The upper sum, which is this bit here, gave us an area of 1 here. So the first one, Riemann's upper sum, the first term would be the 1. But because we're now looking at Riemann's lower sum, hang on, so the first term would actually, this area here would actually be a half. And then the second one would represent this, and the third one would represent this, and so on. So the area underneath the red line, so that's this area here, this whole area here underneath the red line, from one all the way to an arbitrary nth term, from 1 to the nth term. Well, the area underneath the red line would be greater than Riemann's lower sum. So this would be a half, this would be a third, this would be a quarter. But the last one, so it's dot. But the last one would be you jumping to n, and then jumping to n, and then drawing it across. So the last one would be 1 over n times the width here, which is 1. Delta x here is 1. So the last term is 1. Riemann's upper sum, the last term, Riemann's upper sum, the last term would be you jumping to here. Well, Riemann's upper sum, the last term would be 1 over n minus 1. But then Riemann's lower sum, the last term would be 1 over n, because Riemann's lower sum would be you jumping to here and then drawing it from the right to the left, 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 from the right to the left. So the last one would be 1 over n. But Riemann's upper sum would be you starting from the left, moving to the right, starting from the left, moving to the right, starting from the left and moving to the right, so the last term would be n minus 1. The last one would be 1 over n minus 1. But Riemann's lower sum, the last term would be 1 over n. I hope you can follow that. So now looking at our notation Sn. Remember, this is just a notation. Sn is us summing up the first n terms. Okay, so now if you look at this, this is exactly the same as this. So when you look at this, this is nothing more than a notation. This is our notation for us summing up the first n terms. So when you look at this, this is exactly the same as this. So now let's take away 1 from both sides. Looking at this, take away 1 from both sides. So this thing here equals this. Now this thing here is exactly the same as this. So let's put this into here to replace this. Okay, so we are going to put this into this whole thing here. Oops, into this whole thing here. So now we've got this thing is less than this thing here. So now we've got s minus 1. So now we've got s minus 1. Sn minus 1 is less than the area underneath the red line. So now we've done this many times. If you integrate this from 1 to n, it will give you this thing here. So now we know that you summing up, well, let's add 1 to both sides. So that will then give you this. So you summing up the first, hang on, bear with me. So you summing up the first nth term, the first nth terms would be less than the natural log of the nth term plus 1. So basically we are here now. And then in the previous video, we've shown that Sn is greater than natural log. So now you can put the two together. In this video we've established this. In the previous video we've established this. So now we can deduce this. So what that means is you summing up, let's say you summing up the first 100 terms of that series. So 1 plus 1 over 2 plus 1 over 3. You summing up the first 100 terms would be somewhere in between 5.6 and 4.6. So you putting 100 into this natural log here. If you natural log 100 plus 1 will give you this. Natural log 100 it will give you this. So if you sum up the first 100 terms, it will lie somewhere in between here and here. Okay.